Hi everyone. This is lessons 2.2 and 2.3 from our Algebra 2A class covering linear models and correlation. And this chapter, as I've said about many of the other lessons in this chapter, this lesson is a very quick summary of what was really covered in an entire chapter in Algebra 1. Okay, so it's going to be just a very brief overview of what it means to be a linear function and how we can use linear functions to do something called modeling. So a linear function, in its most basic definition form, is an equation in two variables in the first degree. What we're probably used to thinking of is like y equals mx plus b. That's a linear equation, okay? Linear equations are formed by repeated addition. So, I'm starting at 5 and I'm increasing by 3 over and over and over again. Okay, and so there's all kinds of math we can do with this, but we can also use something called a linear model to represent like a real life situation. And sometimes this is based on data, okay? Sometimes it's based on just knowing the parameters of the situation. We know we're starting with this much, we know we're increasing by this much over time, but anytime you're writing a linear equation to somehow represent like a real life scenario, what you are doing is called modeling. And a linear model would be an equation that models a given situation. And then correlation. Correlation is what we talk about when we're working with scatter plots. There's some examples of scatter plots down here at the bottom. And the correlation measures how close the data is to being in a perfect straight line. Because the closer it is to being in a perfect straight line, the better our model is going to be. So correlation is always measured on a scale from -1 up to +1, with 0 kind of in the center. Okay. A +1 correlation is a perfect, strong correlation. Okay. However, -1 is also a perfectly strong correlation. Okay. So how can these both be strong? How can 1 and -1 have the same strength? Well, the only difference between positive correlation and negative correlation is the directions that the dots are heading. Okay, positive correlation has a positive slope, so it's heading upward. Negative correlation has a negative slope, so these points would be pointing downward. Okay, but if they're a perfect straight line like that, that would be a +1 or a -1. Okay, a 0 would be weak correlation. Okay. And that would be if your points were kind of spread out all over the place. If there really wasn't a rhyme or a reason to them, you can't see even which direction they're kind of pointing in, just points all over the place. That's weak correlation. So using that scale from -1 to +1, we're going to estimate what these correlation coefficients would be. By the way, the correlation coefficient, we use R to represent that, and that's just the number that we're assigning to the correlation. So this here is in a pretty decent straight line. I would say it's probably, I don't know, maybe a 0.8, and it's pointing downward, so I would probably estimate this to be about -0.8. This one here looks just like this one, except it's kind of pointing upwards instead, so that's going to change it from -0.8 to +0.8. Now, that's not a hard and fast number. If you had estimated that and said 0.7, I probably would have said that was fine. You're just estimating where 1 is a perfect straight line and 0 is not a line at all. And I'm saying this is about an 8 or a 0.8 on that scale. So something like this one, you can definitely still see sort of a linear trend, right? You can see that the points are heading in that direction, but they're definitely more spread out than either of these up here. This might be, I don't know, a 0.4 or a 0.5, something like that. Okay. And then this one, I really can't even tell if the points are pointing upward or downward. I don't see any sort of line in there. And so this, I would say, is awfully close to 0. Okay. This next statement I'm not going to say too much about right now, just because I know it's going to come up later when we do our statistics stuff. But be careful about confusing correlation with causation. Just because you're saying that two things have a correlation, that just means that they're happening at the same time. It doesn't necessarily mean that one is causing the other one to happen. And so people can misinterpret statistics very significantly by mixing those two things up. Okay, moving on. 2 more words for you. Extrapolation versus interpolation. Both of these have to do with making predictions, and I'm just going to put that up here. This is all about making predictions with data. Because that's the whole point of making a model. That's the whole point of coming up with an equation to model your situation, is that then you could use that to project. You could say, if we continued this trend, what's going to happen in 20 years or something like that. Okay? Here's the big difference. Extrapolation is making predictions beyond the scope of your data. And interpolation is making predictions within the scope of your data. Okay. And I'm going to just do a quick example of that. I'm going to put this here. So let's say I collect some data on time of day versus attention span. So this is time, and this is your attention span. We're going to just measure in minutes. So let's say at 7 a.m., you can stay with me for 30 minutes. Okay, you have a 30-minute attention span at 7 a.m. And then I check in with my students that I have at 8:30. Okay, and they're starting to get a little bit squirrely. Maybe their attention span is 20 minutes. And then I look at everyone again at 1 o'clock, and I see our poor attention span has dwindled to 5 minutes. Okay, I'll just stick with that data. That's enough for now. If I wanted to come in here and say, if at 8:30 my attention span was 20 minutes, 1 o'clock it was 5 minutes, I wonder what it would have looked like at 10 a.m. And so I try to use my patterns here to figure out what would this number have been. That right there would be interpolation. Okay? Because that's within the scope of the data that I had already collected. It kind of falls within that data. I didn't actually collect the data point at that time, but it's within the scope of the data that I collected. If I went down here and tried to project what your attention span might look like at 4:30, let's say, and then I tried to figure out what this was going to be, that would be extrapolation. Because that's asking my data to go beyond the scope of where I stopped collecting data before. Okay, so if it's beyond the scope of your original data, if it's outside of the boundaries of the data that you had collected, that's extrapolation. And the thing you have to look out for is extrapolation is far less reliable. Okay, when we extrapolate, we don't always know that the trend that we found earlier is going to continue. So we have to be careful with extrapolation. Now, I'll be honest, people still do this, lots, okay, with data. There's a lot of times that we collect data and then we try to say, if this trend continues 20 years in the future, what will that look like? We can still get an idea, but we just can't count on it as much, okay, because it's less reliable when we go beyond the scope of the data we predicted, okay? Okay, so let's head down to do one of these. Let's actually do one of these data analyses. We want to find a linear model that represents all of this data, okay? And to do that, we're going to use our calculator. And those of you who had Algebra 1 with us, this should ring a bell. This should definitely look familiar. So on your calculator, we're going to start with stat, and that very first one is edit, okay? And this is where I'm going to enter my 2 lists of data. Now, just to save time, I already did that. So if you're watching this and trying to follow along, I would pause the video right now and go ahead and enter those numbers in. Okay, but I put the cost in list 1 and the rating in list 2. Okay, I entered all those numbers in. And then I'm going to go back to stat. I'm going to go over to calc. And then option number 4 is linear regression. Okay? Now, on this calculator, when I hit enter, it just brings me to that screen, and then I can just hit enter again. That's what I'm looking for. If your screen gives you some other stuff like list 1, list 2, something, I forget what the other ones say, and then at the bottom it says calculate, you just go down to where it says calculate and hit enter. Okay? So, based on this, y equals ax plus b, my linear model would look like this. Y equals let's see, I try not to round these too much, but I've got that 9 in there. So I'm going to go 0.37x plus 41 point, and again, my rounding is going to be messed up. So we'll just go 41.9. Okay? 0.37x plus 41.9. That came from these numbers here. Okay? And then it says, use this model to predict the rating of a $45 coffee maker. Well, this is asking us to take that 45 and plug it in for x in our model. So I'm going to go 0.37 times 45 plus, 41.9. And I would predict that that $45 coffee maker would have a rating of approximately, we'll go 59 because it looks like all of our ratings are in whole numbers. Okay, I'm just going to jot down quick what we just did. 0.37 times 45 plus 41.9. And that gives us approximately 59. Okay. Now, to answer this next question, how much faith do you have in this? How good is this model? We need to look at our correlation coefficient. And those actually should have shown up back here when we did our linear regression model. The batteries popped out of my calculator right before I did this, and that sometimes resets this. So I'm just going to fix that quickly. If you need help in class with how to fix it and you can't follow along with what I'm doing right now because I'm going really fast, please just ask and I can show you how to do it. That is something that once you fix it once, it should stay fixed unless your batteries come out or something like that. So then I'm going to go through the process again. Stat, calc, option number 4, enter. Okay, and so there's those same numbers again. There's the A and the B, but now I have this R squared and R. And this is the number I'm looking at. That R is my correlation coefficient. And an R value of 0.3 is not very good. Okay, R is approximately equal to 0.31. So how much faith do I have? Not much. Okay. And I'm just going to put a note here that that correlation means my model is not strong. So I can still use it to make a prediction. It's just that my prediction is not very good. Okay. Now, let's look at that next question. Is this extrapolation or interpolation? So that $45 coffee maker, does that fall within the range of the data that we collected originally? And it looks like we collected data all the way up to like $50 and $60 coffee makers. So I feel pretty safe saying that this is interpolation. Okay? Because that 45 is within the data that I had collected originally. If I asked you to make a prediction about a $100 coffee maker, that would be extrapolation. Okay, so let's look at this next one. This next one should ring true just like Algebra 1. It should sound a lot like stuff you did last year. We've got a 140-pound woman going on a diet hoping to lose 0.5 pounds per week. Okay, and we want to write a model for Y, which is her current weight, in terms of how many weeks it's been. So here's how I always start this. My weight right now is 140 pounds. Okay, so I start out with a weight of 140. And then I'm losing 0.5 pounds per week. Okay, so that's my linear model. That's a different kind of linear model. I mean, it's still a linear equation, but we didn't use data this time. We didn't actually go to this poor woman's house and weigh her every week and then track the data. This is based on our estimate, what our plan is. What do we know is going to happen here? So then it says, based on this, when will she reach her weight of 132 pounds? So that's my Y value, okay? So I'm going to put that in for Y. 132 equals 140 . Minus 0.5W And I'm going to use the magic of math here. I assume if you're watching this video, you can solve this equation, so I'm just going to jump straight to the answer. We would subtract 140 and divide by the negative 0.5, and you find that W is equal to 16. Okay, so that's 16 weeks. She would be 132 pounds. So now it says, is this prediction extrapolation or interpolation? There was a piece of information that I kind of glazed over initially here, and that's what helps us answer this question. Is that 16 weeks within the scope of the data that our model is supposed to represent? Okay, and the way I answer that question is this model is good for 20 weeks. She was planning on keeping this up for 20 weeks. So if that 16 weeks falls within the 20 weeks, then I'm good to say that this is interpolation, okay? Because it's within the 20 weeks that the model was set up to represent. Okay, that's about it for this lesson. I believe that pretty much covers lesson 2.2. And then the next part of this lesson is for 2.3, but I'll start a separate video on that. So this should get you through lesson 2.2.